all of us know that the industrial community, the industry implementation community and the research community, the academic community and certain ecosystems like the US, of course, and Europe and now recently China have really worked very well in being able to bring the research done in academia and the problems that the industry faces together and thereby do rapid innovation. I'm sure that the early innovations, whether it was a steam engine or even aircraft, started long before thermodynamics and aerospace engineering started. So industry often is ahead, usually ahead of research in trying out things, and in that process they face problems. We're just talking about something about that with Kumar. I'm sure they constantly face problems, and they probably apply whatever knowledge they have and they've evolved. On the other hand, academia in their, they sit quietly in their gurukul or whatever under a tree, and they evolve ideas and they concoct ideas, and many years of learning and teaching and research have given them, they are prepared minds. So if you bring those problems that industry has found in practice with the deep knowledge that academia has evolved over many years of learning, hopefully one can quickly solve problems with the benefit of both. Academia get interesting problems to work on, and industry gets their problems solved quickly. I don't think that ecosystem has evolved in India as yet. I think it's evolving now with companies like Tejas and others whom we are able to talk to. And we would like that kind of ecosystem to be here, which we see in the US and, of course, China now, in Japan, everywhere. So it's with that in mind that we said, and by the way, I just want to take another minute to tell you about one interesting thing. In the 1990s, NSF did a analysis of the major technologies that have evolved over the last maybe 50 years, now 70 years. So they drew what is called a tire track diagram. There was one line for academia, timeline, one timeline for industry, and one timeline for business. And they drew the timeline until the business became a $1 billion industry. And they actually showed arrows going from academia to industry, industry to academia. Interesting was industry to academia arrows, which showed that many times artifacts that industry was trying to develop would help academia in furthering their understanding of the problem and develop it further. And of course, from there to business. They looked at risk processors, they looked at natural language processing, they looked at Unix, they looked at internet, and that is a published document. In 2020, the US National Academy of Sciences brought about an extension of that, which actually extended the tire track diagram to, impact on society and many things. So clearly, those ecosystems understand the importance of this confluence. I think in India we need to absorb that and bring it in. So with that in mind, we have brought together 9 speakers, and Dr. Dhananjay would be chairing the first session. And maybe you want to add a few words, otherwise the floor is yours.
Sounds good. Thanks so much. No, I think Professor Anurag already described how this all started. I'd just like to add just one more thing to it. What we felt was, at conferences, we come in and talk about work we've already done, right? So we wanted to do things slightly differently in this joint kind of forum. So you'll see that a lot of the speakers will be talking about problems that yet need to be solved, right? Examples with 6G or Wi-Fi or whatever. And the idea is to set up problem spaces. And we felt that this was a good way to kind of motivate more cross-collaboration and kind of get this whole thing going, right? So that's about all I would like to say before kind of, starting the session. I think so I think, yeah, we are ready to start. Our first speaker, it's a real honor to invite Dr. Kumar Sivarajan as the keynote speaker for today. Dr. Sivarajan is CTO Tejas Networks. He worked at IBM Watson Research Center, New York, and was on the faculty of the IISc Bangalore before co-founding Tejas Networks in 2000 as its Chief Technology Officer. He has received the IEEE WRG Baker Prize paper, is a distinguished alumnus of IIT Madras, a fellow of the IEEE, and a fellow of the Indian National Academy of Engineering. Thank you so much for doing this. Please welcome him.
So the way we have planned out this workshop is that we'll have 35 minutes for each presentation, 25 minutes for the actual presentation, and 10 minutes for discussion. Please open up, because these people are all experts in their own areas. And I think unless we discuss, we will just have a regular conference session. So there'll be a person sitting right up in the front. Where is that person? Who will show a 5-minute 5 minutes before your presentation time ends. He'll show
it's 503, I got it.
Yeah, and then 0 is when you're supposed to finish speaking, and then 3 minutes before the end of 35 minutes, there'll again be a warning when we should now do a changeover.
Only thing is there's no clock here. So thank you very much. It's a pleasure to be here, Professor Anurag Kumar, Dhananjay. Looking forward to a lively discussion. Okay, let me try to be provocative. So, talking about 6G radio access networks. Okay, so I want to be very clear. It's not about many things that generally get talked about in 6G. So first, let's look at the standard diagram of 6G. Okay, so we failed in 5G to do anything with low latency. Okay, but we can't admit it, so we carried over the thing to 6G and say we're going to make it hyper reliable. So hopefully in 6G we'll do something with low latency. That's the hope, right? In 5G, 0 happened. We also failed with all the IoT stuff. We're supposed to have massive machine type communication. Mostly we're still talking to phones. I can talk to my washing machine now, but it has nothing to do with the 5G network. Okay, so hopefully we'll address this problem, and I'll have tell you some ideas in this. And then because we have 6, we had to come up with 6 things to do. So 3 more things needed to get added, right? It's just a marketing thing. Okay, you can't do without AI. So we have to figure out what to do with AI in communications. I think a lot of you are thinking about it. Maybe we can do something. The other thing we added was integrated sensing. I'll have more to say. But since we added it, I think as a community, let's make a success of it before 2029 or 2030. The top one, somewhere there, is ubiquitous connectivity. This actually India drove. Jishnu from my team was part of the ITU delegation from India to say, day one, we want everybody in India to have 6G, right? So ubiquitous connectivity is a problem because we are, if you live in India, you will know that we assume everybody has mobile connectivity for payments, for anything. OTP is how the country works. So if you don't have connectivity in any remote corner, sort of people can't do things. They can't even transact. They can't buy anything. Okay. So this is something we want to solve from day one. So this is the charter. There are a lot of new applications. I won't spend time on this slide. I think this is where we go wrong. We over-market, put everything, and then when 5G gets rolled out, the operators say, what happened to everything, right? So I think we need to focus. So we need to classify the applications. What matters to a service provider who's the customer for all of this 5G, 6G equipment is what you can do outdoor, pretty much, right? What you can do outdoor in mobile environments. Everything else that gets talked about, extended reality, holograms, remote surgery, if at all they happen, they will happen without any 6G network, okay? I mean, maybe if you do gaming, right, you're going to game in front of your computer. If you have a hologram, so the only thing that matters there is there's a fiber optic network, high-speed connectivity to the room that you're in. Maybe the last 10 meters is Wi-Fi or mostly even Bluetooth in all these applications. So I think over-marketing this as a product of 6G is again going to lead to disillusionment in 2030. So let's focus what service providers can do, which is outdoor mobility. Okay, I think that's. Now, there is something that's quite often talked about, which is fixed wireless. Right? Now, you can say fixed wireless is an oxymoron. Why do you need fixed wireless because you can have fiber or wired connectivity. But it turns out that the problem of wiring that last 100 meters to the home is difficult. In India, you know, we got electricity, but now getting fiber to every home is a tall order, unless you tie up with the electricity company or something, which doesn't seem to happen. In the US, there is penetration by cable. I mean, I'm ignoring the copper because that's not useful for anything. But if telcos need to compete with the cable companies, they can't get fiber to the home easily. Even Verizon doesn't have FiOS everywhere if you go to the website. They would like to do fixed wireless. So I think in developing countries, it's needed to give you reliable broadband, high capacity broadband, a gigabit to the home. Because India sort of thought till 2020 that mobile broadband is good enough broadband. They said we skipped the whole wired generation. We have 4G dongles, and there's a lot of these dongles that go around. That's what the broadband connectivity people had. But once especially in COVID, when people were trying to use this very slim, slender connection for doing children education, on-site browsing and everything, they realized there is a much better broadband that people need. So there is a need to get something equivalent to a fiber broadband through mobile technologies, simply because we can't get fiber everywhere. Okay? So I think that area is worth focusing, even though it's not mobility, and it's not really outdoor, but it's getting that last mile connectivity. One of the missteps, I talked about application missteps in 5G. One of the other missteps was to try to use what is called FR2, which is the 26 gigahertz, 28 gigahertz band. That simply didn't work, right? And it was first tried out in the US. I think Verizon rolled out 5G, maybe 15,000 base stations. Nobody could get anything because it was hardly reaching 100 meters. That spectrum was repurposed from what we would traditionally call microwave backhaul. It's now called millimeter wave, but I won't dwell on that. You can look up why all this terminology exists. So, but this spectrum is there. It is with the mobile operators, and it is crying out to be used, okay? And there's a good application for it, which is fixed wireless. I don't think it works for mobility. So one of the things that we could try to do is to build very good fixed wireless systems, but with the 26 gigahertz FR2 spectrum, okay? And why that, and why not, let's say, the mid-band or 3.5 gigahertz? Because that's valuable for mobility. So this is one of the problems, is make this millimeter wave work very well, right? Now, I didn't address it here, but let me speak to it. One of the issues we face and our operators, customers face is power consumption of all the radios, okay? I'm talking macro radios. So today, the best power efficiency you can get on a high power radio is about 40%. And we typically put out like 160 watts of RF power. So you end up consuming 500 watts per radio, right? And 3 radios plus the base band, 2-3 kilowatts. This is for one band. If you have multiple bands, it's a lot of power. This is becoming a problem for operator profitability. Probably not for AT&T and Verizon, because they charge you $25 per ARPU. Here they charge you $2-3. So I think reducing power consumption will be important. And in millimeter wave, when we started to build this, I realized the problem is even more horrendous. Okay, we can't get efficiencies of more than 5%. So if you want to put out 100 watts of RF power in millimeter wave, we need 5 kilowatts, something of that order. So I think as a community, if you're building something for 6G, see if you can build new waveforms which do not have this requirement to be in the linear regime of the amplifier, right? Because this happens because we put all this 256 QAM and so on, so you need the linearity. I don't know if it's possible, and I think there's a lot of inertia in trying to change the guts of the communication system. We got onto a good thing with OFDM and everything in 4G. We made no changes in 5G, we as an industry, and I think we're looking to make no changes in 6G, but if you do this, all the problems will remain, right? So if you have the courage, try to relook purely from a power efficiency point of view, what can you change with the modulation and coding schemes? Even if you can't change the mobility, at least we can start changing things like in millimeter wave, okay? okay, so that we can go further. So this is one of the inputs that I have, okay. For some time, I used to think, what's the point of beamforming? In fact, I've been in talks to say, do we need massive MIMO at all? What does it buy you? So, after debates internally, I think massive MIMO is a good thing. Okay, it's a good thing because it gives you a very efficient way to trade off between coverage and capacity. So first, I can build one radio. So we did some, like, say, 100 megahertz, which is the popular bandwidth in 3.5. And if I build a 32TR radio, I could get 4 separate beams. This is equivalent to having 4 sectors. Okay, so you could argue that I could just have built 4 radios and built 4 sectors, but this gives me flexibility on where I direct the beams. So that's one option, is I can just take one radio and create out of it maybe 4 different sectors and get the full capacity in each sector. And if somebody happens to intercept 2 beams, he can get even more. The other thing is, I can compromise and I can use all the 32 ports or more or whatever I have to form a much more directed beam, which will enable me to get coverage which I can't get. And things like millimeter wave, we find this is very useful, because if I have, say, like fixed wireless, I can reach out to a far off customer at the cost of capacity, because I could be serving 4 customers instead I'm serving 1 customer, but at least I'm able to serve them, and I can do this very flexibly. So I think massive MIMO has its uses, and maybe it's to do with the fact that I can form multiple beams, or I can form a very directed single beam, and I can do this very flexibly. So I think getting this perfected, I don't think, by the way, all this beam forming, beam tracking, and all that is working very well in practice. Okay, so while you may hear there's a subscriber and it's going to move and I'm going to direct the beam at it, none of that is actually deployed in practice. I think a good place to start would be in fixed wireless, where we could form all these beams and create enough capacity. In mobility, it would almost be static beams. I think some beam tracking is something I think we may be some time away from mastering, but at least being able to do these beams flexibly is useful. So, now the mobile phone has obsoleted many devices. Camera being one of them, right? Kodak went down. So the next target for the mobile phone is the sat phone. Okay, so the sat phone is going to go away, because the mobile will be able to communicate in all the satellite bands. So already all the satellite bands are part of 3GPP, and the satellite folks are scrambling to rejig their satellites to give you satellite, to talk to your mobile phone. This is true of Geo, Leo, and all that. And Elon Musk, who leads all this, I think already has a service to your mobile phone in 2.6 gigahertz. Maybe it's pan USA, or and it's not very expensive. And this is a way to get broadband everywhere. So I think there is a convergence of satellite and mobile, which is almost certain to happen. Now, there are a couple of ways you can do this, right? So you can put base stations on the satellite. I think that's a very expensive way to do things, right? Because first of all, this base stations have to become space-grade equipment. Satellites carry a lot of weight. I think Space Mobile has taken that approach. Probably, whatever Elon Musk is doing today is that. And I think a more pragmatic approach would be to have what is this transparent mode, which is the satellite would relay the signals. Probably one side would use the mobile band, so they're talking to the mobile phone, and the other side would use maybe millimeter wave or the Ka band, Ku band. I don't know the satellite terminology well, but there are satellite bands specifically which may not be used for mobility. I think that may be the way to go. It also fits in well with sort of the regulatory needs. You want the signal coming down, so it can be, the legal, lawful intercept can happen. The government can take a look at it if they want, and so on. Right? So I think from all that point of view, I think this is going to go the way of relaying the signal from the satellite back to the Earth, because governments are concerned about sovereignty. They don't want signals going to satellite and going somewhere off to another country. So I think that's what we can focus on. Then, if it is geo, we have to deal with a huge amount of latency and still get things like voice to work. So I think that's one challenge. Maybe that's not so exciting. But LEO satellites offer you a lot of challenges, because satellites are moving very fast. You have to manage the Doppler. You have to manage the handovers which happen every few seconds. So I think this is a good exciting area for us to work on, assuming we're to provide mobile coverage. I don't think there's a threat to the ground-based network, because sometimes people ask, even my board asks, with satellites coming, are we out of business? So I think this can only at best complement, because the capacity that it can provide is much less, but we can make it a success. And I think it will help us to develop a lot of other technologies. There's more things you can do below the satellite, high altitude platforms and so on, which is basically for coverage. Okay. Can we put low latency to use, at least in 6G? Okay, so in 5G, so what happens is we dream of it, we think we can do it. But if you think about it, everything we thought about low latency was, gaming, but it's not clear, that the delays behind, in going to the game server or whatever, see, the delays in the network, right, may dominate what is the delay in the radio access network, in the rest of the network. So most gaming that I've seen, you play in front of, your gaming machine, and it's a Bluetooth or Wi-Fi connectivity. So I think gaming and all that was the wrong focus. Since 5G, we now have self-driving cars, and you can get a taxi in San Francisco here, which is self-driving. I'm eager to go to San Francisco and try it. I'd like to be driven by a machine. But I think that's coming up. And now these cars drive like humans. I mean, they have LiDAR and radar and everything, but they're looking at other cars, right? There's no infrastructure assist. Now, the infrastructure can assist this self-driving in many ways, right? So first, you're not limited to what you can see. The infrastructure can tell you what's around the corner, right? And so we can see, or we can postulate, that self-driving will get helped by low latency communication, and because the two of you communicating are very close by, right, with other cars, or the infrastructure is next to you. The other thing is drones, right? So drones can make deliveries. I mean, there are issues. It's not as widespread, but Amazon has tried drone deliveries. I think in India also people are thinking about it. And many of these may work like flight air traffic control. That means you'll have a drone lane, and then you'll have infrastructure which directs all the drones to fly. So in these couple of cases, low latency could be useful, but we have to target it for this kind of an application. Okay. I won't spend too much time here, but full duplex is something that we tried to do, right? So tried to say we can double the capacity with full duplex. It didn't quite succeed, because there's a 150 dB difference between the transmit and the receive, and you can't get enough rejection for full duplex to succeed. But now there's something called sub-band full duplex, which is not really full duplex, but what it is in TDD, you can transmit and receive on different slots at the same time. So it's really an exercise in trying to reduce latency, but if we can push full duplex, that would be a nice thing to do, because you double the capacity. But this is where we are on full duplex. Okay. I talked about latency and what can happen in 6G. What can happen with IoT in 6G? So RFIDs have been very successful. Okay, so if you can, ambient IoT, which is talked about, is a replacement for RFID, which can help the service providers to get more revenue. In India, we use FASTag a lot. So thinking, FASTag can be read, but maybe many other things can be read. Maybe you can track goods with ambient IoT. And then there's reduced capability. So camera and video surveillance is important. So maybe if you can enable that application, which is like an IoT, the camera is an IoT device. And NB-IoT never took off, at least in India. And here, I was talking to an operator in the US, he said even in US, NB-IoT has not taken off. And India is trying to do smart meters and so on. So maybe 3 different kinds of IoT devices can take off in 5G. And the operator is looking for additional revenue. So I think if we can focus on making this very successful, because especially in India, the operators have got $2-3 of revenue, 200, 300 rupees of revenue. So they're looking at how can they make another extra 50 rupees or 10 rupees or whatever. All of that helps. So I think some of these things have the capacity, have the promise of being successful. In particular, I think ambient IoT can be useful to track packages and cars and FASTag and so on. Okay. There's one more which is sort of in the standard, but maybe not getting as much attention. We all assume that our location is known very well, right? But it's known very well to Google, because or to whomsoever you share your location with, and it is not known to the operator. Okay, so your GPS location is shared with every app that you have on your phone because they ask for location, and you don't have the patience to decide. So you just say yes, right? And maybe you say while using the app you can have the location. So everybody has a location. Swiggy has your location, Zomato has your location, okay, Google certainly has your location. But the operator does not have your location, okay? And sometimes they say, no, the ambulance guy does not have your location. He should probably talk to Swiggy or Zomato. So one of the things the operators would like is to have the location of the user. And if they ask the user as part of the service, he won't give it to them. There are privacy concerns. But can we solve the problem for the operator and give him the location of the user? This can enable other applications. For example, it can enable a hospital or an ambulance to locate you in an emergency at your room in your apartment. I think this problem is worth solving, but you need to get about 1 meter accuracy in 3D, and you need to get it indoor. So it's sort of the GPS sharing doesn't help. So what you need is really triangulation of some sort across base stations, maybe cooperation. All you have is a mobile phone or maybe a smart watch which is connected to the mobile network. I think this is a problem that the operators would like. I can see that it has real benefits, but we have to solve it. And we're not competing with GPS because GPS doesn't even work indoor. Maybe the last known location is there. If you can get it purely from the operator network, I think this is a useful thing to do. Okay. RIS, yes, 5 minutes, I will end, thank you. So RIS is reconfigurable intelligent surfaces. What it is a way of changing the propagation environment. So we did an experiment in our lab. We are collaborating with IIT Bhilai, where we could, I think there's more stuff here, yeah. So you could, configure this, set of this surface, right? I won't get into details of how, I don't even know, you probably do. So to then either give you a reflection, like act like a mirror, okay, by changing it. So you could, by changing the surface, get this thing to be received here or not. Okay, so you just change how you bias this device. So now this can improve coverage, and it seems to work. So in the initial experiment, we got like a 10 dB difference of signal, if we use the surface or if we didn't use the surface. But I think there are challenges that are worth thinking about. First, there are, of course, challenges at some high level saying, if you modify the environment and your neighbor doesn't get coverage, then what happens? Right? So regulatory issues like that. You can block sunlight to your neighbor. Now you can block even his mobile signal, right, by putting some surface. The other issue is interoperator. You have to configure this. For example, if you put it in your house, then you can do whatever you want. But if the operator were to deploy it, he should only affect his radio waves, right? So Airtel cannot be affecting the coverage of Jio. So given these two aspects as to who deploys and to affect the environment for all the radio waves, can you make it operator specific? I think unless we solve this problem of being something specific to the operator's bandwidth, this technology will not take off. Otherwise, it will go into courts and get shot down. Okay. Since I have only 5 minutes and I don't know much about AI ML, all I want to tell you is that all your problems of channel estimation, deciding what modulation coding scheme to use, the link adaptation, all of this can probably be done much better with AI today. Okay, so you did spend many, many years getting PhDs in communication theory, reading all those fat books. I also taught from some of them. And maybe all of that is not so useful. But the other way to think about it is, if you got trained in all of that, you can use AI better to accomplish the same thing. Okay, so an operator may not care, but I think if you're in a competitive environment, you have to do the best in terms of all the communication algorithms, and you should seek the help of AI, otherwise you'll risk getting left behind. My last application is sensing. I think mobile operators have this huge radio network, and with massive MIMO and so on, and millimeter wave, they have lots of antennas. This is pretty similar to radar, and that's what the thinking in 6G is. So if you can use this network to sense the environment, you could probably create a digital map, a live digital map of cities with traffic, buildings, detect drones, detect intruders, and so on. I think the security agencies will like it, but city governments will like it, and the operators will like it if they can make an extra buck by selling a sensing service, right? So I think this is also something that we can focus on. Some of these applications will involve some kind of edge computing because you can't sense and send all of this back. So maybe others where I talked about camera uplink. So combination of sensing and edge computing could be a new revenue stream. So I will end here. So there are many things we can do, but there are many things we should not do. So I think let's not get carried away by remote surgery and telepresence and holograms. They are of no use. We should I mean, they may be of use, but nothing to do with 6G. We should focus on what the service providers want, right? What they can use and what they can use to make extra money. And that is kind of the applications I've tried to highlight here. So now I'm out of time and open to questions. By the way, before I add, let me answer one. 5G's only accomplishment is to give us broadband in 3.5 gigahertz, so you can get more capacity if you're near a base station. At the end of the day, if you don't do any of this, 6G will do this in 7 gigahertz, not in terahertz, okay? So terahertz is all a pipe dream. So in 7 gigahertz, you will get what you're getting from 5G. That may be okay, okay? Think of, before EVs, what did car industry do every 10 years? You got the 2025 Toyota Corolla. It's not very different from the 2024 Toyota Corolla. We may be going that way, but if we want to do a little better, we can do something like this. Otherwise, there's still a market. Radios have a life of 10 years exactly. So the 6G radios have to replace the 5G radios. Life goes on. Okay, so thank you. Am I supposed to moderate? Okay.
So sorry.
Because okay.
I was thinking about what you said. Thank you so much. Yeah. Sure. Yeah.
I think
Yeah,
that went
I don't
first. 1, 2, 3, and then the rest you have to update.
More of a comment than a question. You had mentioned edge computing. I face these issues while working in Ericsson. Edge computing is really basically the, shall we say, elephant in the room, which is generally ignored. Because if you see the growth of distributed computing and cloud computing, it happened only because there were certain few companies made the massive investments in hardware and building scale-out data centers like Google, Microsoft, Amazon, and so on, which propelled the growth of distributed computing, cloud computing, etc. So somebody has to really make this kind of a massive investment in edge computing and figure out geographically what is the most optimal way in which you will set up an edge computing infrastructure in a city or in a state or in any locality, for example, or any district, things like that. And that is something that is really missing because that's one that is really needed for 6G.
Yeah. Okay. Thank you.
And great talks. Thanks for being so frank. I really appreciate it because we ask these questions from industry folks. We generally get politically correct answers. So thanks for being open about it. The comment/question I have is, the comm networks are very successful, but essentially it took two proven markets and made them mobile. So speech or voice was already a proven market. Telephone existed, and they made them mobile. And then internet was already successful, and we had wireless internet, right? Now, is there another market which is already proven, you think, which we could then do? And that may be the way, because we know that somebody is willing to pay for that market.
Yeah. See, I think there are very smart people outside of our community, and we must admit they're way smarter. These are the people who created Google and Facebook and WhatsApp and AI and so many things, right? So as communication engineers, we do our best. We look at what capabilities we can provide, okay? And then hope that somebody else will leverage it to do something really earth-shattering or whatever, life-changing. So I think that's all we can do. Now, if we sit here and try to say, what is the next social media application, what's happening? There are youngsters in high school who know this better than we do. So let's be.
I think.
Yeah, I think he had the question.
Question.
After that, I leave it to you.
Okay. Sure.
Great talk. Thanks. I really enjoyed your perspectives. I'm Gaurav. Right now, I do my own thing, advising startups. In my past life, run 5G product line for Cisco. So I've seen this story play out and everything that you said in terms of the story and the 5G use cases not really taking off. And the way you classified this in terms of outdoor mobility and fixed wireless makes a lot of sense. Those are the things that service providers need to focus on. Those are the use cases. Everything else that 5G focused on is a pipe dream. For the rest of your presentation, as you went through the use cases, when I really think about a lot of those use cases, are they going to be addressed with capillary networks where it's probably not 5G or 6G, which is the last mile? What's your thought on that?
So I tried, and I have failed in some cases, to try to look at applications which can be addressed with the mobile network. If you say location, I'm really thinking that it's a cooperation of all the base stations that you deployed that will help this. If you say sensing, I'm looking at the outdoor networks which can sense the environment. Maybe in some cases I misstepped, but that was the intent. That it is not the capillary. The Internet of Things at home, the smart home, all that has happened. It has happened through Zigbee and Bluetooth and Wi-Fi. Literally, I can talk to my washing machine now. I can switch it on. But that has nothing to do with the 6G network. So we focus on things that the service provider network can do.
Okay. So I'm basically system and solution architect, and I have come from the field. I use the technologies which you all develop, okay, whether academia and the industry. So one of the puzzle which we are still trying to solve, and I think you alluded to that through NB-IoT, like smart city or the civic infrastructure, and it's an outdoor and mix of semi-indoor also. Some nodes are semi-indoor. You can't control the location on the like smart meters. You can't control the location. So they are not readily accessible through the mobile networks. NB-IoT, as you rightly said, they have been attempted, they are failing because it cannot meet the expectations. So what is the right kind of technology or mix of technologies that will solve this puzzle? Because we are looking at power consumption, we are looking at throughput, range and all that. And do you think it's a mix of the wireless PAN and whatever? Because we are still trying to make a combination. I think cellular operators, they say no, your wireless PANs are not right, and because they want to sell the NB, but NB-IoT is failing.
Yeah. So as I said, I'm looking at service provider as the customer. There are a lot of things that will happen without the service provider network. I think this PAN is the personal area network we talked about. A lot of home automation happens without it. So be it. There are different applications. So there is no need to force any convergence. At the application level, you have convergence. You can access your WhatsApp on this thing. So I think I'm not looking at some convergence of everything. I'm just looking at what can we do to help the service provider do a better job in 6G and make more money than we did in 5G. So it's a very narrow focus. It's not addressing the wide scope that you talked about.
Okay, thank you.
I think we can ask one more question.
Anurag, I have a question.
In your presentation, there was no mention of private 5G or private 6G. Is that an important direction, or it's one should ignore it?
I think one should ignore. Okay. Okay. See, if you look at the whole market size of private 5G, it's very small. Okay. I looked at a big steel company. In their whole mine, they need 4 base stations. So first of all, it doesn't scale. So if you want to deploy, you can deploy. But it usually be the operator who will just deploy for the mine or whatever. Inside a factory, to automate the assembly line and all that, you can use Wi-Fi or you can use wired for the most part. Okay? So the more I look at it, I see that this is again something that we're trying to over-market by saying we'll do industrial automation and industry 5.0, 6.0, I don't know what the current number is. Okay? So it's not required. And if it can be done, it will go the way of home automation. Okay, which is done with some other technologies. There are some outdoor cases like mines and campuses and so on, which can be served by some private 5G, but that's just the operator deploying the network and letting you keep the data inside and all that, right? So you can use your mobile phone on the campus and avoid your internet, but that's really an application level thing. I don't think there's any new technology that is needed for this.
Sure.
Might
Yeah,
take-
one more. We can have one more.
Kumar, thank you. It was a great talk. So I want to focus on something you said at the very end about one of the biggest accomplishments of 5G was we figured out how to use 3.5 gigahertz.
Yeah.
And I'd like to ask you about 7 gigahertz for 6G, right?
Yeah.
So in the US, they're kind of still mired in figuring
Wi-Fi.
out how to even allocate spectrum because of coexistence with satellites. So
Yes.
what is the thinking in India? Perhaps you can comment on that.
I have not followed it, but I think some new spectrum will come for 6G. I'm aware that there's coexistence with satellite issues. In India, there was an issue even for 3.5, right? So that's why we blocked off 3670 to 3700. And then there's also Wi-Fi. People want all of this to be made available for Wi-Fi. So I am not keeping on top of the spectrum because I have a very narrow view. Some new spectrum will come. We'll build radios in that band and we'll call it 6G. Okay. So the spectrum debate is to be handled by operators because they need more spectrum to compete with the satellite providers and so on. So that's my view. And I remember I said 7 gigahertz, not terahertz, because I think terahertz is not going to happen in 2030 timeframe. Okay.
You know,
If you have, there's a last question, but if we're out of time, we're out of time. I'm 11:14. Yeah. Okay.
I think, okay, I think we'll probably stop. I think there are multiple questions coming up. Right,
Okay.
so, you know, thank you so much for that very frank presentation of your perspective on where the industry is. Thank you also for painting, you know, so many open areas for, you know, for people to work on. That is, I'd like to reiterate, one of the key goals of this session, to kind of identify exactly what you did. Thank you so much. You know, let's please thank you.
Say a few words about what we are giving. It's
Yes,
only
please
a-
go ahead. Yeah, please.
Huh?
Yeah.
It's only a piece of cardboard. There's no sandalwood or any such thing in there. I'm sorry. So I don't know if all you know, the Praveen Bhagwat has been cultivating a forest in nearby Pune. And essentially what he's doing is he is going to plant a tree in the speaker's name. And the speaker can track the tree's growth by pointing his camera or her camera at the QR code. That's what this is about.
Oh, that's very nice. Yeah, yeah. Thank you. Okay, I think we can move to the next talk. You know, I'd like to welcome Dr. Rajat Prakash. The title of his talk is Digital Twins and Wireless Applications. Rajat is a very old friend. Many of them are, by the way. But Rajat has been with Wireless Research and Development Group at Qualcomm. His current work focuses on construction and applications of digital twins of wireless networks. He also works on Open RAN and industrial IoT for 5G. Now, please welcome Rajat.
All right, thanks Dhananjay for the introduction. And so this session, the theme of the session is very good, creating new cooperations between industry and academia, identifying problems which are open from an industry perspective. So what I'll try to do today, talk about a theme of research I have been working on, which is digital twin, which is different streams of research come together. Underlying, we'll talk about wireless as a common theme, but it talks about convergence of different themes across modeling technologies, machine learning, computer vision, and so on. And often in research innovations in academia, it's about different perspectives coming together to solve a problem which ultimately creates value. And that has been a tradition in all our engineering departments in all the top schools. So hopefully people will take some account of converging different technologies to trigger some new innovation. So I'll have a couple of slides up front about Qualcomm, what we do in terms of our corporate approach to partnership with universities. So we have a university relations program. And if you if you go to Qualcomm's website, you'll see some of the activities we do there. So we partner with many universities, conference sponsorships, and we are active in multiple countries. And a lot of the partnerships we do, we talk one-on-one with different schools, with different professors, and we talk to them about problems Qualcomm is interested in solving. And I think this platform here today is about a bigger platform outreach to more people to say what are the problems we see are interesting. But on a individual level with universities, this is a tradition Qualcomm has been doing for a long time. And I assume every company has their own way of working with universities in more one-on-one settings. So yeah, so we partner with universities, with professors, with students. We have different kinds of innovation fellowships, and we have different areas of technology we focus on, all the way from machine learning, automotive, and spanning through till wireless. So that's the very high-level view of what we do in our partnership with universities. Let's get to the focus of the talk, which is digital twin. So let me give a quick introduction on digital twin. What is a digital twin? What's the definition of a digital twin? And then we'll spend most of the talk talking about how it relates to wireless technology and ultimately driving value for some of the stakeholders in wireless technology. The stakeholders are the end users, the service providers, the technology vendors. So using technology to drive value for different stakeholders. So if we look at digital twin, essentially, let me start with this picture. So we have a physical instance of an object. It could be a machine, it could be a network, it could be a process, it could be a spacecraft. So that's what we call the physical counterpart. And there is a modeling technology to model the behavior of what that physical system is doing, which is called here a virtual representation. This picture is from the recent National Academy of Engineering paper on digital twin. And given different people were approaching digital twin with a slightly different definition, slightly different perspective, the US National Academy of Engineering came up with this definition. So we all talk, when we think about digital twin, I think generally people have this thing in idea that there's a physical system. You're trying to model that physical system via either emulation, a simulation, a data-driven neural model. So there are various modeling techniques, and you could have a statistical approach, a mathematical approach. Emulation is a more of a software technology. So there are various underlying technologies how to do this modeling. And what's the purpose we are trying to achieve? So that's captured in this definition. So we are trying to create a virtual information construct corresponding to a physical system. We want to mimic the structure and behavior of that system. In our case, we are looking at it as an engineering problem, not a digital twin, let's say from a social science perspective, so that's a different stream. From an engineering perspective, we are really trying to model the structure and behavior of an engineered system, something we made ourselves like a wireless network, like a robot, etc. We want to model this behavior in an accurate and representative way, which means we are trying to continuously gather telemetry from the physical system. And the telemetry is making sure that the modeling is, has a as small as possible gap between what the model is predicting versus what the real system is doing. So telemetry and dynamically updating the system is very important. And then we want this virtual representation to have a predictive capability. The predictive capability ultimately has to lead to decisions that realize value. So a digital twin modeling technique, but modeling with a purpose, modeling with the intent to create value. And as a result of creating value, we ultimately have to have a closed loop. So there's a physical system, we gather information from it, we do modeling, and then to create value, you have to go back into the physical system, and that's where you create value. So it's not creating virtual value. The idea is to create real value by taking actions which inform what the physical system is doing, how you manage it, how you update it, maybe your operational cost, maybe your KPIs associated with that system. That's what we are trying to improve. And the digital twin from different, these are work streams in the digital twin consortium, which is not really a standards body, but more of a technology promotion body. Digital twin as a modeling technique has been used in various industries, started by NASA, as many great things are. So started by NASA, I think about 40 years ago, as a digital twin of a spacecraft for human flight, but then adopted by other industry segments who are trying to build physical systems that are really valuable. Physical systems that are really valuable, it could be an MRI machine. So General Electric is building an MRI machine, and they will sell the hospital a digital twin of the MRI machine. It could be a wind turbine, it could be a jet engine. So its background is aerospace, heavy industry, heavy engineering. As the modeling as a technology matures, as telemetry capabilities mature, and people want to realize the same value which these other industries have realized with digital twin, we want to realize the same value in our industry in wireless communications. So can we do things for less cost? Can we improve our KPIs? Those are the questions we are after, and applying this technology to our industry. Okay, so let's look at what our industry does. And I'll start at the bottom of this slide here. So what we are trying to do is collect information from a real wireless network, which could be, you can think of as a 5G network, 4G network, and then going forward, a 6G network. We want to collect inputs about the context of that wireless network. Classically, you would construct what's called in the industry PMs, performance metrics. So you would collect, okay, what are my call drop statistics? What is my handover failure statistics? And operators, of course, are very interested in managing these performance metrics. So this is the kind of data you can collect. You can collect RF measurements, the signal strength, the Doppler, all kinds of measurements from the RF domain. And you can collect information about the spatial environment where the network exists, a 2D map, a 3D map, maybe a camera feed, maybe a CAD drawing. If a network is deployed in a stadium, you could have a CAD drawing of the stadium. There could be sensors which are collecting information about the physical world. The sensors could tell you areas where there is a traffic overloading, maybe a highway congestion, and integrated sensing, which is also one of the 6G themes. You could have radar type of information coming in. So we want to ingest all this information into the central block here, which is a digital twin. So there's a technology convergence across GIS, where the maps come in, computer vision, machine learning, sensor fusion. You want to ingest all this information, and it's sort of a Niagara Fall of information data coming in. You need to be smart about how to manage it, store it, and so on. And model the wireless system. So you want to model the propagation, you want to model the network. Modeling the network is a challenging exercise because the wireless network is pretty complex. It has a scheduler, which a lot of us in the, let's say, more research side, we are used to doing research on various scheduling techniques. It has modeling of the propagation, admission control. Really, if you want to create a good digital twin, you have to model the backplane, which is a lot of the latency where it comes from, the routers, the core network. So there's a lot of modeling to be done. And then you create also a digital representation of the physical world, which is where computer vision, where CAD modeling and GIS come in. So once we do all this modeling, the end goal is to create value. What is the value we are trying to create? One value is improve efficiency of the wireless network we are building this digital twin for. So we do all this modeling with the objective of improving either network management, some MAC procedure, positioning accuracy, channel modeling at the channel frequency response level, the channel impulse response level. So we are trying to see, do better modeling, can we improve these things? So at Qualcomm, we have been looking at this, and there are some very, I'd say, new problems in this area, which I would encourage people in the academic side to also take a look at it. So that's on the left side. On the right side, it's about, again, I think the theme of creating value for the service providers in our wireless communications industry. So can we say we are going to provide, as a result of better modeling, are we able to provide better services? So spectrum management, for example, there is coexistence in, for example, in India, the example was between satellite and terrestrial users. By creating a digital twin of the system of interest, the wireless system terrestrial, the wireless system space-based, by creating a digital twin, can we achieve a higher resolution of sharing of spectrum? And examples, I'll cover a few of these examples in detail. Can we improve some of the much talked about applications like XR connected with the 5G or 6G, public safety, presence detection? So we like to think of it as, on the left, improving the efficiency of things we do already. On the right, trying to do new things and things which were not even possible before. With a digital twin, can we do it now and generate a different set of value there? Okay. So this is a representative view from the ITU. This picture is taken from the ITU document on digital twin requirements. And the ITU is looking at it from a perspective of what are the applications. So from a wireless network, can we do better deployment planning? Can we model the user experience in a digital twin to really prove that what 6G technology might be able to offer? There are some technical areas to look at. So the main message of this slide I want to leave you with is that the digital twin applications for wireless is a pretty compelling area of interest in the standard side. In addition to the ITU, 3GPP, O-RAN Alliance, and IEEE, they are all looking at digital twin applications into wireless. They have, though, started looking at it relatively recently. So in my view, it's a promising area of research and questions which previously may not have received attention. So it's a good theme with this workshop, I believe. The next few slides are going to talk about what we at Qualcomm on our industrial research side, what we do. So in a lot of these kind of questions where we are trying to say, can you really create value? Can you really model a wireless network? You can do things theoretically, and then once you have some idea, you try to build it out. So here we try to build out a digital twin of a small scale wireless network. This is a small cell wireless network deployed. Here's a 3D CAD model or a 3D mesh model of area we have. It's a warehouse building we have. And I believe at ISC might be something closer to what Art Park does, though I've never visited there. So we have a 3D model of this building in San Diego. And we used bunch of sensors or data acquisition tools to build this 3D model, LiDAR, camera, fusion. Once we build this 3D model, we modeled the RF equipment we have there, the antennas, the small cells. We created, in the digital domain, we did propagation modeling. So propagation modeling is a great complex technology in itself. It involves ray tracing, GPU usage, electromagnetics modeling, wave theory, all kinds of things. So we did that modeling, and we did measurements. So the blue and the green dots here tell you how the modeling is comparing with the measurements. And the promise of the digital twin is you want to do modeling which is reasonably accurate, and then it will save you from doing a lot of measurements in the field because you can do a lot of things in the modeling domain without incurring the cost of doing things in the field. So in this case, we did this modeling, and then for the specific network we have, it has 8 small cells. We asked the question of, can you use a modeling technology to predict the throughput a user will actually see? So in this example, after all this modeling, we were able to show that in the modeling, the throughput, we had 4 users, the throughput of this user will be 120, and then the modeling said it's pretty close. So this is a proof of concept that modeling for wireless networks is feasible. And the way it ties to value is if the operator is asking, what is the user experience, what is the number of users I can actually sustain in a particular network. So let's say the operator asks, I want to add this new band which the regulator made available. If I add this band, what will I actually get? So there's a bunch of modeling technology to get there. Okay? So another example we looked at was, this is getting into machine learning applications. So by using digital twin modeling, one of the promises of digital twin is the ability to create synthetic data which is relatively realistic. So it's not synthetic as in some hexagonal layout of cells with all the towers at the same 17 meters height. It's a realistic modeling. So in this realistic modeling, we create a synthetic data set, which is a data set of signal strength samples. In this case, we had a robot which was moving around. But we could do that in the digital domain, in the modeling environment, and we created a lot of data sets of what would the signal pattern look like. Using that signal pattern, you can create a machine learning model and train it in digital domain. Once it's trained in digital domain, you can deploy it into the real world, and in the real world, you can assess its performance. What's the value? The value is training a model in the real world has a high data acquisition cost, and it has maybe a power consumption, maybe a MIPS, and so on. So the intent is, can we train models in the digital domain, deploy them in the real world, and still get reasonable performance? So this is what this experiment was showing. In the handover case, the model did what we expected it to do. I guess in this case, 4 times out of 5. One time we had some loss. So, and that's the way, I guess, to approach research. You need to say, Now, why did we have this loss one time, and then you go deeper into the problem. But the basic idea of doing data-driven design, machine learning design with a use of synthetic data and then validating that in the real world as a concept that applies to so many streams, even though here it's just done for a relatively well understood handover mobility problem. Digital twin for positioning, again, this is talking about RF fingerprinting as a technology. So the theme is the same. We create data in a synthetic domain. So you can do modeling to create a fingerprint database, which is entirely synthetic. You can train a fingerprinting neural network on that, which is going to tell you if the input is the signal strength, what is my location estimate. So those kind of neural networks have been in the literature for the last about 5 years, that you try to train a network and you query it for the position prediction with the input signal strength. The challenge with those kind of networks have been to train it, you need a lot of real data. And to get the real data, you have to do, you have to have engineers in the field, you have to have people doing drive testing, and so on. So in the digital data, you can avoid all those problems. Okay. So here is one of the research areas getting closer to some of the physical layer problems. So in 3GPP and in ETSI, people have been spending time on high-resolution channel modeling. And high-resolution channel modeling means trying to model the channel down to the clusters, the multipath, the angles of arrival, trying to create a realistic view of what the channel will look like. So let's say we look at this, in this cartoon example, there are some buildings and some cuboids. So create a channel model corresponding to this specific intersection of these two streets, for example. Create a channel model specific to that area. Can we, when we talk about machine learning aided design for algorithms in the wireless space, we typically use statistical channels, which are coming from your PED-A, TDL-A, TDL-B. But can we use synthetic channels which are not purely statistical, which have grounding in some real network where ray tracing propagation modeling was done? Can we use those channel models to now revisit some of the traditional questions of wireless systems? How do I do channel estimation? How do I do DMRS design? How do I do beam sweep design? Again, using synthetic data to do stuff, and then going back to the real world, trying it to see whether you improve performance. It also applies to what we would commonly think of as core physical layer procedures, such as RS design or beam sweep design. Spectrum sharing, again, it's one of the more intuitive fits with digital twin, and there are some examples with the CBRS band and AFC in Wi-Fi in the United States. In Europe, LSA is under study, in Italy and France, I believe. And again, if you're trying to do high resolution or dynamic sharing of spectrum between multiple users, the maturity of modeling technologies becomes very important. And digital twin is essentially a modeling technology with the attempt to be as realistic as possible. All right. So I'll just close with this slide, and this is the previous set of slides was using digital twins to improve what wireless systems can do and the traditional KPIs. This slide is a bit of a, let's say, a vision slide to say other industries use digital twins. So smart cities, they have a digital twin of the smart city. For example, Tokyo, you visit their website, they have all the 3D modeling of all of Tokyo in extreme detail. And the city government of Tokyo is trying to use that to improve the services they provide. Whether they are trying to provide their citizens better emergency response services, street cleaning services, whatever it is. So they know what they are doing. Can we help them to do what they are doing? Can we help them more? So whether it's smart cities, autonomous transportations, immersive reality, all of these industries and technology domains, they are approaching digital twin modeling from their perspective. And the wireless industry or wireless connectivity and the services we bring, how can we enable them better? So what kind of connectivity do they need? Are they happy with the EMTC, NB-IoT, or they want 6G to do something different for them? So that's another topic to investigate, engage more with other industries to find out what is really needed. So I'll close with that one.
Thank you so much, Rajat. I think we'll throw it open to questions. I think there's one here.
Just a couple of observations. From our experience, my name is Shiv from Microsoft. digital twins have been more successful in planning and design oriented applications, whereas it appears here you're also trying to use it in dynamic situations. So I'm just curious how effective do you see there? That's part one. The other area we see very attractive in applying machine learning in the context of digital twins is the new area of applying directly modeling physics in AI, neural networks. And we are getting very good approximations for some particular domains. Just curious whether you're thinking about applications. So these are two separate points.
So for the second question, the one where physics-inspired areas is propagation modeling. There's quite a bit of research happening in that area, and propagation modeling, you could either use solve the full differential equations with the wave, or you could do shoot and bounce approximations. And there are people in machine learning research, I mean, some of them in Qualcomm too, who are trying to approach, let's say, purely neural models to propagation modeling. You can think of that as physics-inspired research, whether it's like a nerve, but for wireless. So that's, I think, a pretty open area. I don't see any good solutions yet, though. And I think the first question
The first one was about how effective is it for dynamic situations?
So I think on dynamic situations, what we would like to do is model, let's say, fault prediction type of use cases, where the digital twin is telling you that you already modeled some scenarios, and now you are seeing those scenarios unfold in the real world, and you are prepared to react. So an example of that would be, you are seeing in the real world, there is a congestion in the network in a certain area, and the digital twin already knows what kind of response strategies work well if you see congestion in a certain way. So let's say there's a sports event and there's a congestion in certain area in the network. In the digital twin, you have already done a lot of what-if strategies and so on. So it allows you to better prepare and respond to dynamic events as they happen. Hopefully there's also more. So there are a lot of open problems there.
Yes, I think there was, yeah.
Thanks for a wonderful talk. My name is Nilesh from IISc. I had a question kind of related to what Shiv was asking, but much more from a physical layer perspective. Twice you mentioned beam management as an application for digital twin. And the question I have is the time scale of operation of the twin. Typically, beam management, the way I understand it, it's tens of milliseconds. You need to switch your beam, select your beam, recover from a failed, a millimeter beam. If it fails, you've got to recover. Is it possible to operate at that time scale using digital twins?
So most of the uses of digital twin are when you get to the 10 millisecond time scale, or let's say sub-second time scale. The role of the digital twin is to prepare strategies in a modeling environment and deploy those strategies into the real world. The response in the 10 millisecond to 1 second time scale, that response should not involve a round trip with the digital twin itself. The digital twin has prepared, so in the ORAN industry, for example, we have the X apps. The digital twin can prepare a strategy and push that strategy down into an X app or into a base station scheduler, and the response has to happen there. But the modeling of beam management scenarios well in advance can happen in the digital twin.
Hi, Rajat. Yeah, great talk. Let me just focus on the physical layer, computational EM deterministic ray tracing approaches versus all the historical statistical approaches. Here's a question I have asked, found no answers, I'm sure. There's a reason we do the statistical. With the deterministic approach, you get an answer for exactly that scenario. If I do a little perturbation, you have to recompute. So ideal marriage is between the both.
Yes.
Have you found any reasonable approach to marry these two?
So
different, but
I wouldn't say we have found the answer to that, but the way we are approaching it is in terms of mixing these two approaches. We are looking to create a data set, which is a data set created in a synthetic domain, and then apply statistical techniques on top of that data set. We are not looking to do, at a specific location, do a electromagnetic modeling for, for this device, and then try to see what will happen to this device. But we could do a statistical modeling of what's happening, let's say, in this room, and try to build on top of that, trying to get to a specific device and a specific location. Maybe the next step after that.
Thanks, Rajat. This is Ashu again. So one way, one could decide to do something and say, hey, there's this upper bound or some theoretical bound. And where we are today are really far away, and I need some new ways of doing things, right? And so, is there a pressing case like that which comes up for digital twin where we are operating today is so far away from where we could be? So, for example, scheduling or channel modeling. I think we can, I don't know whether you have seen benefits of better modeling beyond what we do today, which is actually also an approximation which is data-driven. All channel models are data-driven anyways, right?
So I can give you maybe one speculative answer and one answer which is more grounded. So on the more grounded one for positioning, we do see that creating a relatively realistic channel model in an area of interest does help to improve positioning outcomes, whether we are doing ranging-based positioning or RSSI-based fingerprinting, because the problem is inherently tied to the spatial mapping of the channel. So that, I think we are comfortable with that conclusion. The more speculative one would be, you could think of, all of us when we studied information theory, the upper bound is perfect CSIT, perfect CSIR. So can the digital twin get you there? So I think that's what's a question from Sumit. Not anytime soon, but that's a kind of upper bound where you could say we are still, as our industry, we have not met that bound yet.
Hi, nice talk. I'm Ashwin from the University of Helsinki. I just wanted to know how much information about the environment do you need? For instance, if you have to do a digital twin of this room, do you need to know the type of material of the walls? Do you need to know what is the height of the walls? There are these AC vents and so on. So what would be the taxonomy, or how do you address this problem of the environment? Because that can affect how the wireless signals, or in this context, the wireless signals might also propagate and see the reflections and so on.
I think it's one of the broad open problems in this area. For different use cases we are trying to do with the digital twin, the answer would vary. And trying to understand that range. Some use cases would be in a low resolution category. Some of them would demand, let's say, intelligent reflective surfaces. You might want to do very high resolution modeling, but not very well understood area at this point.
Okay. One more question if there is, or else we will close this session, this particular talk. Okay, all right. Well, thank you so much, Rajat. Thank you. Yes, our next speaker is Dr. Rohit Kapoor. Rohit is part of the wireless R&D team in Qualcomm. He leads wireless R&D and systems engineering teams at Bangalore. During his time in Qualcomm, he has been involved in the design, development, standardization, and commercialization of many key technologies that are part of 3G, 4G, 5G, cellular, as well as Wi-Fi, wireless LAN standards. So please welcome Rohit.
First of all, thank you, Dhananjay and Professor Anurag for setting up this forum. Really excited to be part of this. I think it's a pretty unique way of doing this, getting industry and academia together, and hopefully it spurs some interesting discussion as well. Yeah. Okay. So maybe before I get started, my previous two speakers, of course, spoke on cellular, and I have the interesting job now of making Wi-Fi research look somewhat cool as well, right? So, but I'm going to take a stab at it on what are some of the interesting problems that Wi-Fi faces today. Some of them are, of course, problems that cellular is already looking at, or cellular may have looked at. But the nature of Wi-Fi is that a lot of problems that get solved with cellular in some way, they get adopted in a future version of Wi-Fi as well, though in a slightly lesser sophisticated, lesser complex way, right? And there are good reasons for that. Having spent time, some of my early parts of my career as a researcher on cellular, along with my colleague Rajat, and then some of the later part on Wi-Fi, I'm able to appreciate some of the differences in the approach to these two technologies as well, right? Cellular, there's a lot of money that goes behind it in terms of research investment. Wi-Fi also, but certainly less so than cellular. So that's one big difference, right? So any solution that we come up with for Wi-Fi, one has to keep in mind that cost has to be a factor, and cost has to be significantly lower than whatever we introduce for cellular. So that's something that absolutely has to be at the back of our minds when designing something for Wi-Fi. So that's number one, right? The second difference, at least at a very, very sort of 30,000 foot level that I see between cellular and Wi-Fi, is that Wi-Fi fundamentally works in unlicensed spectrum, right? And what that means is that, before transmitting, you have to carrier sense, right? And, that apparently simple thing of needing to carrier sense leads to so much, you can say, difficulty or complexity in solving problems of latency, right? And I'll touch upon some of that, right? So, if we want to approach Wi-Fi problems, I think it's really critical that we keep these two things in mind, that cost has to be a factor. Whatever solutions we come up with, they may not go as far in getting you like 90% of the gain. Maybe it's good enough to get 60, 70% of the gain out of a feature, but that's important. And the second thing is that latency has to be handled, or the solutions for latency have to be done in a very different way from cellular. So with that in mind, my plan for today was to maybe take a step back, just walk through what's been done for Wi-Fi at a high level over the last maybe 2 or 3 decades, and where we are. Where does that leave us? What are the problems in front of us, right? And I'm going to motivate sort of 2, 3 problems that I myself have seen as a Wi-Fi researcher, that Wi-Fi standards and products out there have taken some steps towards solving, but I think they are far from solved, right? Okay. All right. So, goes without saying that, Wi-Fi has revolutionized the way we access the internet. Simple things, right? I think when some of us were in grad school, maybe early 2000s, they were like wires all around, and kind of that really used to be the state of our houses. In fact, I remember having done some of this myself, right? Like plugging multiple cables to our routers, Ethernet cables, to connect them to different devices, right? And compare and contrast that, to the world that we have, sort of today, right? Okay. So now, just a little bit of background about Wi-Fi. Of course, we see Wi-Fi as complementing cellular connectivity with a lot of focus on local, broadband access inside the home, inside conference rooms, generally indoors, right? Though some outdoors as well, but with generally sort of focus on indoors, right? And one interesting thing about Wi-Fi is, as I mentioned, is that it works in unlicensed spectrum, so 2.4, 5, 6, and there's been some standardization in 60 gigahertz as well, though commercialization has not been as successful, but still, it attempts in sort of, to go towards that, right? And just to reiterate that, right, the fact that it works in unlicensed spectrum really brings out the fundamental, you can say, aspect that makes it different from cellular, right? That we have to really, really focus on if we want to solve some of these forward-looking problems for Wi-Fi. So I'll just wanted to touch upon that, a lot of things here, but the main takeaway, for me, when I look at Wi-Fi, is unlicensed spectrum and the need to do carrier sense. So, everybody, any research on Wi-Fi, something to keep in mind. Okay. So, again, this is a sort of a long story about Wi-Fi, maybe last couple of decades or even more, maybe 2.5 decades. Not going to walk through this, but really sort of 2 things that I want to touch upon is that, if you look at sort of the initial generations of Wi-Fi here, right, the focus was really to try to push more bandwidth, more antennas, higher modulation, the usual stuff that all of us will do as communications engineers. And, that served its purpose really well. In fact, even today I find people, I'm sure you do as well, who are maybe not so much from the engineering field, who will upgrade their access point just because it has more antennas, right? And that's a great thing for us, by the way, right? I mean, no complaints about that, right? But I think if you look at the last couple of generations of Wi-Fi, there's been some focus. Of course, there's the usual focus on increasing spectrum, higher order, modulation, more MIMO, all of that stuff. But there's also some focus towards, these new kinds of applications and how do we support them better. And good examples of that are, for example, OFDMA, right, which allows you to support, many users at the same time with lower latency, or users that have, smaller packets, shorter packets, all those kinds of things, right? So you can see that we spent a lot of time sort of bulking up Wi-Fi here. We're still bulking it up, but we are also taking some little bit, you can say, smarter or little bit more focused features into Wi-Fi that solve some very specific problems. And the reason I touch upon that is that the rest of my talk, I'm going to build upon that a little bit. Okay, so let me spend a few minutes on this slide as well. It gives a little bit of a sort of a history, a perspective of, again, how we got here. Of course, some of the initial generations of Wi-Fi, the Gs and the Ns, MIMO, OFDM, all of that. Wi-Fi mesh itself, not so much a standardized feature, but as Qualcomm and other companies as well, I think we played a critical role in bringing that to market. And that's really important to be able to solve, home-wide sort of coverage issues, right? And that was one sort of very interesting innovation, that was brought to market. Beyond that, as I mentioned, there's been focus in AC and AX on not just bulking up the Wi-Fi standard, but also in bringing some interesting specific innovations like OFDMA, MU-MIMO, and so on. And one thing I do want to touch upon is that there's also been some, let's say, standard forays towards standardizing the 60 gigahertz spectrum in the form of, or use of 60 gigahertz spectrum in the form of AD-AY. It's something that I think we've tried to commercialize in many ways, but so far the market hasn't quite taken off. But we still see that that's a pretty important sort of arrow in the arsenal of Wi-Fi technologies, right? Just wanted to leave this overall view, and you'll notice also that I'm also only covering till Wi-Fi 6 here, because I'll spend the next couple of my slides touching upon Wi-Fi 7 and a little bit differently, and what does that bring to the table in terms of the applications in front of us. Okay, so now if you look up to Wi-Fi 6, right, we've brought in all these innovations, we bulked up Wi-Fi, we've added features such as MIMO, MU-MIMO, OFDMA, all of these features, and by and large, there's been pretty good adoption in the market. I would say the industry has done a reasonably good job of anticipating users' needs and sort of bringing to bear features that by and large, help the consumer, right? Sometimes, they actually help in improving performance. Sometimes it's a little perceived, but be that as it may, right? Users, there has been good uptake of these standards, right? But we are at the point now where if you're a user, who's actively using Wi-Fi, you expect that whether you're in a crowded area such as this, you're in a stadium, and we've all had this experience, right? That wireless connectivity generally doesn't work very well in crowded areas such as stadiums in India, right? Yeah. So I think users have this expectation that they should still be able to make a voice call, a video call, or upload pictures. All of that should still happen even while they are in crowded environments, right? So that's kind of one thing to keep in mind, right? In terms of evolution of Wi-Fi, users have this expectation that even if you have multiple devices, multiple users, Wi-Fi should work as well, right? So that's one problem I feel that does face us in Wi-Fi, and how do we solve that, right? A second thing that I want to touch upon, going back to the latency thing, is that a lot of the applications that we see coming up, there's of course, gaming that's existed for a while, but also newer applications such as, XR, based, where latency is again of central importance. And in fact, for applications such as XR, it's kind of unique in the sense that it's an application that requires low latency, but it also has a significant requirement of throughput, right? And you can contrast that with gaming, which is a very low throughput application but requires low latency, right? So XR really requires the sort of it's the envelope, right? It requires high throughput but low latency, so very hard problem to solve, right? So the takeaway from this is that we've reached a certain point in Wi-Fi, and I think to really kind of help support the next set of applications, we need to take some steps towards supporting multiple users, doing multiple low latency applications. That space of problem, we need to attack that, right? And maybe before going into how Wi-Fi 7, takes some steps towards that, right? I just want to spend a little bit of time on talking about what is the definition of latency that we're talking about here, because I think this is a little important, and it's something that as part of my work, I've also, sort of had the chance to think about this a little bit more. So if you look, generally, if we try to look at some of the features that we've added into Wi-Fi, because they lead to higher throughput, they lead to higher average latency as well. I mean, that's a given, right? But what we are talking about here is not just the average latency. What we are talking about is that, if you look in Wi-Fi, oftentimes there'll be outlier events, right? Things will be working well, and then suddenly for like half a second, your video will stop working, right? Because packets got delayed or whatever, right? Or there's interference from a user that's trying to access the medium, right? So I think the question in front of us for some of these applications, such as gaming and XR, and video conferencing and some others, is really a focus on what we call tail latency. And the idea there is that, not just the average latency, but your 95% of packets, or even in some cases 99% of packets, they need to be able to meet a latency bound. And you can see, that when you pose that problem and you put together with that, hey, Wi-Fi is actually like a random access carrier sense type medium, is very hard to put them together. They don't really gel well together, right? And I think that's really the problem that I think whatever innovations we can make in that direction, I feel will be golden, right? That's a very interesting problem to solve, right? Now, one or two other things to mention is that, from a user point of view, right, what does latency mean? Let's spend a little bit of time thinking about it, right? So of course, if you're doing a voice call, it's the time taken to deliver your voice packet, or time taken to deliver your video frame. But you can also think of some other things, like for example, if you're a gaming user, right, and you have a controller in your hand, right, that controller transmits some information to the PlayStation or Xbox console, and it's that latency as well that's important. And you can see that latency, of course, reducing average is all good, but the tail matters, right? Because it can't be that your average is good, but 10% of the time, your packets are not getting to the PS5 console in time, right? So I think the key takeaway from this is that, we've put in a lot of features to reduce the average latency. Wi-Fi 7 has taken some steps to reduce the tail latency as well, or to reduce these outlier events, in other words. But I feel there's more work required here, right? And especially in the context of when there are multiple users, present in a room or in a house or whatever, right? Okay, so now what does Wi-Fi 7 bring us? Maybe I'll touch upon that a little bit. Of course, it's the usual stuff: wider channel bandwidth, higher modulation, all good stuff. There's some interesting techniques. They help in some ways because they just help the system be a little bit more agile. Like, for example, multi-RU OFDMA, it gives the scheduler some more flexibility. So all of this generally helps towards the system handling these kind of latency sensitive events better. But for me, the one feature that we added to Wi-Fi 7, which we call here simultaneous multi-link or alternating multi-link, in other words, it falls under the category of what we call multi-link operation, MLO. That is one feature that really helps to reduce latency, and I want to talk about that a little bit. Okay, so how does this work? And I'm showing one sort of example of this feature called alternating multi-link. There's few different flavors of this in the standards, and anybody who's following Wi-Fi will see that there's 3-4 versions of this, but I'm just picking one of these for now. So what alternating multi-link does is that it allows you to, for every packet, that shows up, right? It allows the AP or simultaneously, similarly the stay, to access on 2 different bands at the same time. And on whichever band you get access earlier, you're allowed to transmit the packet, right? Simple as that, right? And you can, very simple maths, very simple probability, you can show that this can cut down tail latency hugely, right? I mean, given some conditions of, interference and so on, right? So now this feature is of course now standardized. It's also in our products out there, starting to gain traction. We are showcasing to all our customers how things like gaming, XR can really see improvements from this, right? So this is, I think, one step that Wi-Fi 7 has taken, towards this direction of cutting down, what we call tail latency, or keeping that under control, right? Okay, so having said this, maybe let me just leave this for 1 second here, and I'll come back and sort of try to tie it all together. But can't have a talk without AI, so I do want to touch upon AI a little bit as well, and the relevance of that when it comes to Wi-Fi as well, right? So this is kind of a standard AI slide, but what I really want to touch upon is that what's happening today is that there's a lot of AI happening in the cloud. There's all these LLMs and, students and others are starting to use them in very, very interesting ways, and so on. But what we do see is that, we do see a space for on-device AI as well, what we call edge AI. And we see these two working, edge AI and cloud AI, working together in some kind of interesting way. How it happens, we have to see over the next few years, right? And there are many reasons for this, because users will, of course, want their data to be local. For example, there could be reasons of personalization, security, all those kinds of things. And you can imagine that some of the models, machine learning models that you're running, they run on your edge device. And whenever they cannot run there for whatever reason, because of TOPS or other reasons, that they go to the cloud, right? So we do see that some of these things will start to happen. And the natural place for them to happen is, of course, your Wi-Fi AP, right? So I think we do see that Wi-Fi AP is really a sort of a natural edge AI device, in addition to something like your phone, of course. But Wi-Fi AP is something that's there in like hundreds of millions of homes around the world. So we do see that iterations of these, will start to have some neural processors, GPUs, all those kinds of things. And then the question in front of us is that what are the, in what way can we use these AI processors to make Wi-Fi better? So I'm just leaving it as a little bit of an open problem. It's an area that all of us are thinking as well, right? And really there are sort of two very broad areas you can think about it. One is you can say that I can use presence of AI to improve my Wi-Fi network performance, link performance. I think some of the previous speakers also touched upon that. Imagine having a Wi-Fi mesh deployment in your house. You can easily see that AI models can help optimize those in many interesting ways, right? But the other area one can also think about is sort of adjacent to Wi-Fi. You can imagine that there are other things that start happening in your house, or in your office, for example, just because an edge AI processor is present and it's present in your Wi-Fi AP, which are adjacent to Wi-Fi. It could be positioning, it could be maybe some language-based things. So all of those things that are, that may not directly impact Wi-Fi standards, but they are still part of the Wi-Fi box, right? So anyway, having said that, I think this is my last slide, and what I wanted to leave everybody with is, at least in my view, having seen Wi-Fi over the last few years, these are what I see as some of the interesting problems, right? One is, how do you support applications requiring low tail latency? Gaming, XR, and XR has this interesting property, as I said, that it's high throughput as well. It's not like gaming, right? So how do you support that on Wi-Fi? How do you do that while accommodating multiple users? So how do you innovate Wi-Fi to get there? And the third thing is, what are use cases of AI at the edge, whether in terms of making your Wi-Fi link or network more efficient, or other adjacent to Wi-Fi type of use cases. So I feel that from a Wi-Fi industry point of view, these three are very, very promising areas, and any sort of approaches that help to make progress towards these, would have a lot of value. Yeah. Thank you.
Thank you, Rohit. We have questions here.
So do we see any feasibility of getting time synchronization, or maybe at least the measure of the controlled latency, measured latency, if not time synchronization, which may not be feasible because of whatever low latency we may achieve, but any measured latency, so that, because we have a lot of application where we need time synchronization, and we may not have wired networks.
And you mean synchronization, you mean across APs? Is that what you mean?
Across, the end nodes. So one end node to another end node using Wi-Fi network.
Oh, using Wi-Fi network.
Yes.
Yeah, I think, in fact, we've had some internal R&D efforts also towards those areas, which have, interesting. I think the thing about Wi-Fi in the end, again, like I mentioned, right at the outset, right, because I was following the cellular speakers, right, is that cost is always a factor, right? So, so anything that drives up cost, generally, I mean, it's still great from pushing the technology point of view, because it may be expensive today, but 5 years from now may not be, right? But still, I think so. That's something, something to keep in mind. Right?
So, when you say latency, mean, tail, can you put some numbers onto that? What is the expectation for, say, XR?
No, this is a really good question, right? And So Professor, our understanding of this continues to evolve, but I'll put some numbers to my best understanding, right? Maybe there are 2-3 categories here, right? Gaming, there is XR, and then there are like other applications like the voice video type of application. Maybe I'll start with voice video, right? Because those are better understood, have been around for like decades, right? So voice, typically the latency we talk about is couple hundred milliseconds end to end. Similar for video because it's all driven by voice. So if you have a live video call, couple hundred milliseconds one way end to end is generally a good number. Anytime you start to go beyond that, you'll start to notice the lag, meaning you'll start to talk over each other. And there's a lot of tests, a lot of data that's collected, to support this, right? The second area is gaming. And gaming, again, there's a lot of variation, but the tightest sort of requirements in gaming, which will be like first-person shooter, and there's a lot of videos about this, right, that if you're late by a few milliseconds, you'll miss your target, where the other person will hit the target, and all those kinds of things, right? But the tightest requirements there will be like 5 to 10 milliseconds. 5 to 10 milliseconds at the tail, right? So it's a really, really tight requirement, right? Especially given that if you're in a random access medium like Wi-Fi, if you don't get the medium once and an interferer wins the medium, it's gone for a few milliseconds, like 4 or 5 milliseconds, whatever is the length of transmission, right? So it makes it a very challenging problem. Now XR, again, it depends, you're talking VR, AR, but again, the tightest latency requirements there are of the order of 20, 30 milliseconds, right? But then they are coupled with like very high throughput requirements, 50, 100, or even more Mbps, right? Yeah.
So one more question. So typically, these applications like those that required 5 millisecond, 10 millisecond will be paired with other applications which are also going on, right? Somebody is doing a laptop download, somebody is doing email, somebody is doing something else.
Yeah.
So I suppose one is expecting these very tight latency bounds, mean and the tail, in the presence of other traffic.
Yeah, no, so what you're saying is true, but so it depends on how these things are deployed, right? Because if you, take a typical PlayStation in your home, right? And I have to confess, I have gained this experience only because my kid plays, right? And I see how he does it, right? But if you look at the network they create, right? They'll create a completely different Wi-Fi network, from your home Wi-Fi network, right? So they'll pick a channel that's different, right? So in some sense, you're not competing with your home Wi-Fi. You may still be competing with other Wi-Fis living in apartment communities and so on, right? So yeah, hopefully that's the.
So all these aspects like Edge AI, XR, AV, VR, these have been also been talked in 6G. Do you think the challenges in 6G and Wi-Fi are going to be different or the same?
I think I'll, see at a high level, the challenges are similar, right? Because you have to support similar throughput, you have to support, similar latency. I think the difference is this, that ultimately Wi-Fi will work well indoors, it'll provide you good, XR experiences there. Whereas I think where we see the XR market headed, especially, you would have seen some smart glasses from Ray-Ban and some other companies also coming up now. There's no reason to expect you would only wear them at home, right? You would certainly wear them outside as well, right? And, of course, Wi-Fi will not be able to support that, right? So in some sense, it's a mix of Wi-Fi and cellular that has to support the entire, gamut of XR use cases. Yeah.
Rohit, nice talk. More a researchy question. Towards the end, you'd mentioned about multi-link. And now people are talking about even beyond Wi-Fi 7.
Yes.
So how do you see multi-link evolving?
Yeah, that's a good question. So, few things that you may have seen. Actually, I didn't spend too much time on Wi-Fi 8 because it's still, a lot of things are in flux. It's still going through standardization. But one of the things that's likely going to be a part of Wi-Fi 8, for example, is the ability to coordinate systems a little better, right? And what I mean by that is that, say if you have n APs that are, let's say, present in this room as an example, right? And if all of them are trying to access, right, there's that many more accesses compared to a system where, let's say, one AP accesses, and once it wins, it can share the results of that access, with other APs, right? So it's like creating a little bit more coordination, little bit less reducing the number of accesses in the system. So, these type of techniques will naturally build on multi-link, right, to provide sort of further reduction in latency. Right?
I have one question. This is Bhuwana from Wisconsin.
Yeah.
So you talked about Wi-Fi's next steps. There's a lot of research going on in the area of human activity detection. Do you foresee that to be part of Wi-Fi chipsets, and in what way?
No, absolutely. And in fact, this third pillar that I have here, right, use cases of, AI at the edge, right? certainly. I mean, it's a very, we've traditionally, of course, as Qualcomm also, we've looked at solving those, and I have to say that without AI, you can go some distance, but you still get some false alarm misdetection, right? And I think the promise of AI is that with the right amount of training data, that you can solve it much better.
If you, quick one, yeah. So if you kind of look at the trend of physical layer growth in Wi-Fi, right, and then actual delivered spectral efficiency, which is MAC overhead of sorts, access overhead, they basically reach, access overhead is beyond 50%, right? You kind of lose most of the physical layer throughput just because of random access and other mechanisms. Is that bridging, is that being addressed by other access mechanisms like scheduled access or coordinated access?
Yes, absolutely.
Do you see that? Because that seems to be a bigger chunk one can gain out of it rather than just pushing the physical layer.
No, so I agree with you, and I think maybe being a little, I'll take a slightly different view of it, right? What you're saying is absolutely correct that there are innovations in process in Wi-Fi 8 and certainly beyond as well, which will reduce the overhead, where we try to coordinate the system a little bit more. But having said that, I think it's also important to understand what sells. Right? So if you go and tell a user, oh, we have a coordinated system, I don't know if they understand that, right? But if you tell a user, oh, I'm giving you, higher throughput, your Netflix will run faster, that's it, right? So in some sense, we have to do both of these, right? We have to make sure that the more marketing-y type angles to, to evolution also continue to evolve, right? Yeah.
Great talk. So sort of kind of an extension, and I agree with you, the marketing angle as well as the research side. You mentioned a couple of times, rightfully, that Wi-Fi by nature is random access, carrier sense, and that leads to many of the latency issues and things like that. So my question on that is that nature of licensed versus unlicensed, or is that just because that's the network design? That we are all used to, that's how Wi-Fi works versus cellular?
No, that's a really good question, and I think the answer is really the licensed versus unlicensed. That's the fundamental starting point, right? Because the moment it's unlicensed, you have to design a certain way, and then everything builds on top of that.
So sort of, I mean, I get when it's unlicensed, the way we are used to thinking about it, that anybody can get into the unlicensed, and random access carrier sense makes a lot of sense, but sort of this coordinated scheduled network access, which is what cellular networks do.
Right.
If we think of a Wi-Fi network from scratch, is that possible? Like the design of the Wi-Fi network itself?
Yeah.
I feel like the random access is worst case design. I always assume that somebody is going to be there, and that worst case design.
No, you're right. And to be honest, it's not just worst case design. I mean, the reason that worst case design comes is because of government requirements. Is because there are specific requirements for you that for which you need to do that random access, right? But to the points that you are saying, and I think Professor Anurag, I recall some research from him also in the maybe 6 months or a year back. I think there is certainly interest in moving towards scheduled coordinated systems, but you cannot completely move away from random access because ultimately you have to meet those government requirements, right? But within the space allowed by that, sure, you can move to more coordinated.
Okay. Yeah.
Maybe just to repeat the point, Shrikant from NanoCell. In standards, there has always been PCF and its extensions.
Yes.
I think it's left to the market to actually implement those kind of schedule systems, and market has not bitten that for various reasons. I'm sure Qualcomm can provide answers for that. So it's not lack of standards, but I think the way things have gone, keeping all interests in perspective.
No, I think that's also true. And you're right that PCF, in fact, PCF has existed as long as DCF, I guess, right? At least 20 years, right? So it's true. PCF never took off, and maybe the use cases were such then they were just cable replacement. But in some sense, what we are trying to do in Wi-Fi 8 now is you can argue it's PCF repackaged in sort of more good, with better names and so on, right? So yeah, it's true. Yes, true. Yeah, true. Yeah.
Sure, yeah.
So sub-gigahertz Wi-Fi, we have been looking forward to it for quite some time, but why it has not taken off, and what is the way it could take off really? What are the challenges and concerns, and why? Because we found it with the range and everything.
Sure, yeah. I think at least my understanding of this, I think some of the other cellular experts probably have a better idea than me, is that that spectrum is just too good, right? It's a very nice spectrum, right? So I think that goes towards cellular then, right?
So it's not unlicensed spectrum. Wideband is not available.
Yeah, exactly.
Okay, fair enough. Thanks. I can understand.
Any one last question, if there is, or else, yeah.
So I want to add to that PCF thing. We have NRU and LA, right? They also try to do it in a coordinated fashion. So are they like picking up, or are they like a threat to Wi-Fi? What exactly is happening there?
Maybe I'll defer to Rajat for that question. He's a
Well, adoption is slow.
I mean, I'd like to point out there's no such thing as Wi-Fi spectrum. This is unlicensed spectrum.
unlicensed.
And so long as you adhere to the regulations, you can radiate there. Right? So threat versus no threat, I think you have to think of it like that. Right? Yeah. Okay, thank you so much, Rohit. Okay, we will move on to the next speaker. Please welcome Professor Bharadwaj Amrutur. Professor Amrutur is professor at IISc. He chairs the Robert Bosch Center for Cyber Physical Systems, an interdisciplinary research and academic center in IISc. His current research interests are in tele-autonomous intelligence, where advanced communication networks, along with generative AI and robotics, can potentially transform multiple sectors. Please welcome Professor Amrutur. Can you hear in the back? No, we can't.
No, okay.
I think it's on. Maybe you want to fix the volume.
Okay. Okay, maybe I'll use this one. Yeah, okay. This seems to be better. So how can wireless networks help participate in this ongoing AI hardware revolution, right? And bring in more autonomous capabilities in operations across different sectors. I'm particularly today going to focus on applications in factories, warehouses, etc., right? Where robots are starting to get used more and more.
Sure.
So this is something which, taking off from what Rohit presented in his slide, we see this hierarchy of compute which is there. Your on-device, which has a small brain, your robots, your edge devices. And then you have an edge cloud, an on-prem edge cloud, where you can actually put beefier GPU servers and have more compute. And then, of course, you can go to the cloud, and then you have access to all this awesome capabilities. And the thing is that if I have very low latency available,
then it makes my life as a system designer much easier because I have more degrees of freedom. I can actually push a lot of my compute to the on-prem edge. Why I say the on-prem edge? Because a lot of the data is very sensitive, especially in many of these applications. And if you can solve the problem keeping the data locally, then certainly I think that would be much preferable. The other thing out here is that a lot of the data streams will be videos and images. Videos, images are like the camera is like one of the most, I would say, powerful, versatile sensor, right? You can use the camera to create a lot of other kinds of virtual sensors by doing image processing, AI, etc. on the image stream. What this, of course, means is the requirement on the network. We need very high upload or uplink bandwidths. We'll have a lot of devices, which are cameras, creating a lot of high bandwidth data, so we need high uplink. Typically, the networks have been designed for high downlink bandwidth, but we want actually high uplink bandwidth. And many of these applications like robotics and also, as Rohit mentioned, AR, VR, the round-trip latency, glass-to-glass latency, that is from the camera I pick up to maybe displaying or taking an action, we would like that to be less than, about 50 milliseconds, maybe 100 milliseconds, right? So it's a very stringent requirement, and hopefully Wi-Fi 7, 8, and 6G will solve that problem. In parallel to this, I just want to kind of illustrate what is happening on the AI world, and I think it's very synergistic, right? We had a lot of advances in inferencing, so the models were used to actually give you answers, classify things, and so on. And now the models are doing longer horizon planning, reasoning, and things like that. But what is interesting is that you can actually now, with wireless and communication networks, actually you have AI agents which work together, which collaborate in real time. Humans collaborate, but it's a little bit longer latency, but you can actually now start building systems and thinking of building systems like this, which is really interesting. And if you look at these AI systems, the way they have evolved, you kind of had these systems optimized for inferencing, and now they are doing planning. And then as we go forward, the planning can also use representations of the real-time data, which is digital twin, right? And I think with that, what the digital twin brings to you is enhanced situational awareness. And using that, hopefully the systems can do much better, right? So, so I'm going to focus on, my kind of interest currently is around this, the digital twins, how to build this, and how to use this, right? Just to kind of illustrate out here an example, right? Imagine that you have a warehouse, and then, normally the robot which needs to go takes this path illustrated in red to go and pick up some crate and get it back. Right? But let us say that something happens and there is a spillage of things out here. Right? So, of course, the assumption I'm making out here is that there is a coverage of this warehouse or factory or whatever with a lot of sensors and especially cameras, which is not too unreasonable. People are putting surveillance cameras all over the place, right? Now, the thing is that what is interesting is that this is where semantics also comes in. I mean, the same scene, if I had 2 or 3 people standing versus a crate, boxes fallen down, right? There is a difference in meaning. When a box falls down, for it to get cleared is going to take time. Whereas if there are people here, maybe they'll move around, right? So in terms of when I do my planning for my motion of my robot, the robot has been given a task to come here. When this kind of situation happens, it can replan right away, saying that, look, that aisle is going to be blocked, I need to take a different path, right? So that is much better, it saves much more time than coming here, then realizing you're blocked and then backing out. So this is what is situational awareness, but it's also bringing in semantics, because you're make your understanding what happens and understanding the implication, right? So that is basically the key out here. The semantic knowledge helps you to do reasoning and understand what is the implication of what happened with the changed context. So, so how do you build this semantic digital twin, right? And, I'm kind of just showing out here, so we have been starting to think about how to create like a general platform. And this is where, I kind of look forward to collaboration with people who are working on these kinds of things, because I see an opportunity to create a general framework with opportunities for creating an open framework, allowing for the ecosystem to contribute and develop stuff, right? So things like, of course, you have to start with applications. What do you want to really use this for? Material movement, which I described, is a very important, I would say, low-hanging fruit in many of the industries. They want to automate material movement as soon as possible and remove humans from the loop. And then, of course, being able to kind of walk through a facility, whether it's a construction site, whether it's a factory, etc., through an AR, VR type device, or even an XR type device, right? Safety alerts is another very interesting, important application. And so what is this kind of a platform? So here, with due apologies to Kumar, I've used 5G, but as I said, I'm not hung up on a wireless technology. Anything which gives me very high bandwidth and low latency is kind of what we are really looking for. So, of course, all devices, you have cameras on robots, a lot of fixed cameras, a lot of other IoT devices which gives me telemetry information, and, over a stack, a private 5G stack or a Wi-Fi stack, which really leads to creating this semantic digital twin, which then is used to create this reasoning engine, right? So I kind of use that and kind of do reasoning to give me a kind of a higher level representation of the situation, which then can feed a lot of downstream business applications which can use that and solve the specific business problems, right? So just to kind of illustrate, let us say you have a warehouse, and there is a person who is supposed to manage the warehouse. And then this is the top view of the warehouse, which is a semantic, which is a digital twin, as well as right now just kind of representing the warehouse. And you have this live sensor stream, right, from many, many, many cameras coming in. And that data has to be fused to update our knowledge or belief of this semantic digital twin. Now, and this is knowledge which has to be coupled with some prior knowledge or understanding some existing models, etc. And I'm using the word KG out here as a proxy for knowledge graphs, right? So we kind of know that knowledge is all interrelated, and some kind of a graph type structure might be needed to actually capture this. And of course, this then feeds the real-time state to the reasoning engine, which then uses it to plan the activities, right? You might say that, okay, prepare and consign and dispatch a consignment to some company, right? That is what the warehouse's job is. And it kind of goes through and figures out what it makes. There is some, of course, there's a lot of traditional planning, which is possible, plus some amount of AI to handle kind of new kinds of data streams which are coming in. And then, of course, when you have that, you kind of use that to manage downstream processes like logistics, and then also within the warehouse robot fleet for managing the movement and so on. And each of these can also separately feed off the state which is out here. As I said, the robot fleet movement can subscribe to the situational awareness state and then do a better job of its navigation and planning. So I think this is where I feel there is an opportunity for kind of a collaborative partnership to evolve some common framework which can then be used by multiple players in the ecosystem, right? So, I hesitate to use the word standardization because it's not easy, but if you have a community come together and use it, and eventually it will become the standard. Now, what are the challenges out here in such an activity, right? I think a very important challenge is the representation. How do I represent the information, right? What is the form of representation which will enable many, many different downstream use cases, right? As opposed to getting locked into one. It has to be optimized enough so that I can solve my downstream use cases fast, but it has to be general enough so that a diverse set of use cases can be handled, right? For example, if I were just interested in robot navigation, my representation would take a certain form where I'm just interested in knowing where obstacles are, as an example. Whereas if I want to do a VR, AR walkthrough, not only knowing where they are, but how they look also becomes important. So you see that these two different applications have different requirements. I mean, I'm just putting out here some kind of a graph type structure perhaps, but also time series, because it's evolving with time. But I don't really know an answer to this, right? And then this graph cannot just be graphs with simple nodes. The nodes also need to have embeddings, etc., so that a downstream AI engine can actually do reasoning much better. How do you actually build that kind of a reasoning engine, right? Because what we need to do is we need to be able to predict the future a little bit. And so, you can do, and of course in the AI world there are many possible approaches for doing this. And of course the whole Gen AI stack is there for doing that, but so that prediction is kind of important, and it's kind of also, as I said, tied to the representation as to how that kind of representation gets interpreted by downstream reasoning tasks, right? And one of the things is, when I want to predict, these are very complex structures, right? It's not just one machine or the motion of a particle where I can put a Kalman filter. Here, of course, I might have some physics. I might have, of course, and also business process, which is also very interesting, right? Because you have people involved in a factory, you have other things happening. So if something happens, for example, if the crates fell down on the aisle, it triggers a certain business process of someone getting alerted, someone coming in, all that. So my model has to keep track of that and be aware that that kind of thing happens, right? Plus, of course, common sense, right? So this is where, as human, we kind of expect certain things to happen, and so common sense is also an important ingredient for this. And so how to kind of incorporate all of this as part of my dynamics model of the system is kind of to me, it's an open question. Then there is an issue of scale, right? We would like to, like a factory or this hotel out here, I mean, the number of elements out here is huge. And if you want to create a digital twin of entities of this scale, or kind of scaling out to even a city or a country and so on, I think that is a real challenging task. And how to kind of handle the size, the latency, and both for building it and kind of consuming it is an open question. There is a lot of dynamism. Things are changing, so incorporating dynamism becomes a problem. I'll just, and then there are a couple of other challenges. I think I'll just speed up a little bit. Handling failures, and how to create a digital twin, I need a lot of sensors, right? And this is more of a business problem. How do you justify investing money to actually do this? So I want to kind of talk about one particular approach to representing, which we have been exploring. Our interest is that we want to enable both visually rich applications like AR, VR, as well as enable applications like robot movement, right? And this is where we find this concept of three-dimensional Gaussian splats as something really interesting tool to actually represent the information, right? And as I said, we want to enable visual fidelity as well as enable other downstream applications like robot movement. And this is the new kid in the block, right? So a lot of excitement, a lot of people looking at this. And what are these Gaussian splats? So here is kind of a view of representing a scene. Using this, typically in 3D, you would have what is called a point cloud, right? A point is kind of representing a color and a certain location at a certain location. And you'll have this dense point cloud. you can imagine a point cloud now generalized to a Gaussian balloon, right? It's a Gaussian, it's a 3D Gaussian. It is a 3x3 covariance matrix to describe its kind of shape. It has a center, and there are some colors and so on, and you can actually represent, instead of a point cloud, a Gaussian cloud like this. And what is interesting is that while this was initially developed with a view to be able to synthesize a scene from any particular perspective, people have figured out now that you can actually also use it to capture semantic information of scenes, right? And hence, you can also now use it for doing mapping for robotics and so on. And let me see if this video plays. Okay, sorry, this video is not playing. But just to kind of show, this video was about, was supposed to show you how the scene would look from many different perspectives, right? And of course, there is a trade-off in terms of quality of the rendering and the time it takes to build that model, right? And that is a trade-off which, which as an engineering, it's an engineering trade-off, and one has to kind of figure out how to actually do the right trade-offs, or maybe even allow for trade-offs to be changed dynamically. So what is a typical pipeline which is needed for fusion, right? So you have the image stream or sensor data stream. You might do some kind of pre-processing, filtering, low-pass filtering, maybe certain multi-scale sampling. And then, of course, you might extract features. So traditional computer vision would have this vision type features, but now you can actually pass it through powerful models like SAM and CLIP, et cetera, and extract more higher level semantic features from this, right? And now you have this image augmented with these features, and you want to reconcile it with the knowledge you already have so far of the world. And this is typically posed as an optimization problem. You have a certain knowledge, you predict what might happen, you get some data. That is a typical, kind of, you would say, example from a Kalman filtering update. Predict and optimize, right? And then you store that optimized version as the state of the world in that particular time step. And there is a lot of compute required in this pipeline. And because we have high dimensional data coming in and from many different sources, and you have to handle that, how to actually do this is a challenging problem, which I think it's yet to be solved, right, for large scale. Now, just what is involved out here is that these Gaussian balloons, I'm kind of showing two Gaussian balloons out here just to illustrate, and every Gaussian balloon has these parameters. How opaque it is, what is its location, this is a 3x1 vector, covariance is you can say it's again a 3x1, but it's a 3x3 matrix, color, which is RGB, and then the feature. Feature could be a semantic feature, some feature. And that could potentially be very high dimensional, 128, 256 dimensional vector, right? And the way this works is that, there's a little bit of math, but it's like the whole Gaussian, at any point the opacity is essentially given by this Gaussian equation out here. And then you kind of basically, if I'm looking at this scene from a particular perspective, you project that particular scene using the location of the camera out here, which is the camera pose. You project it, right? And this is a nonlinear operation out here. And then when you project this, what happens is that you end up with a representation of the Gaussian, which is like you kind of like flatten the Gaussian, right? And the important thing out here is that people have figured out how to do this really fast, okay, on the GPU. And that is why this has really caught the attention of many people out here. And you have to do some transformation because you kind of put it out here. But the important point out here is that at this particular pixel, given at U, I can now use these Gaussians and the colors of these Gaussians along with the opacity to kind of tell me what is the effective color which I see in that particular pixel. Okay. And really the most critical thing is that equation for calculating the color is differentiable. And because it is differentiable, I can use my machine learning frameworks, which are really optimized for solving, and I can learn these parameters very fast. And that is really why this has actually taken up. I have a loss which is telling me, given my current belief of the world, what is it that I expect, which is CU, but what is the ground truth, which is CGT, and that difference you minimize by doing gradient descent, and I can do that fast because again my whole pipeline is differentiable and I can really do it very fast, right? And so because of this, this has become very popular, and you can actually build these representations fast. And on top of it, as I said, given an image, you can extract semantic features. So these are labels, semantic labels. This is a person, footpath, road, car, etc. And powerful models have been created now which do all this for you. And then you can actually do the same thing. You can create a semantic loss also now, and you figure out what is the right semantic label in each Gaussian, which will create the semantic loss which I've observed. Right? The key challenge is how much memory you store, because you might have like hundreds of thousands of Gaussians. And if you have 128 dimensional vector tool, it becomes a challenge. And how long does it take to even learn this? So these are some really important problems. And by the way, this kind of technique can also be used to model wireless radio frequency environments, which some people have started looking at. And this is some work done by my student where he found out an alternative way for lifting the semantic features into the Gaussians much, much faster. Right? He claims 2 orders of speed up, and basically the idea is to kind of, every Gaussian has a certain projection into the different images, and then he uses that to kind of come back and do some kind of voting out here, right? And again, I'll be happy to talk more about it later. But what he's able to do is that, if you ask the question, where is the plant in this image, and then he's able to extract the plant very nicely out here, right? Using his technique. And he says, okay, delete the plant. He's able to delete the plant from the scene. So now you are able to kind of take scenes. There are semantic labels in 3D space, and you can do stuff with that, right? This is just one example of what stuff you can do with this. So, as a year, I'll just kind of go really rapidly because I'm kind of nearing the end of time. But given such kind of representations, what can I do? So one of the applications we have been looking at is how to enable better robot motion through localizing the robots better, giving them better plans, etc. So in this particular work, I'm just going to talk about how you can use this kind of knowledge you have gained from fusing information from multiple cameras, etc., to help a robot know where it is in a more precise way. And so the idea is to actually, robot has its own sensors, but you use the cameras also to kind of figure out where the robot is. And you pass that additional piece of information over the network to the robot. And then you fuse that information. So you pass that information along with the covariance matrix, which captures the uncertainty. And then there are standard ways of fusing information streams with different covariances on the robot. And, this is the pipeline which actually does that. Maybe I'll kind of skip going through all the details of this particular pipeline out here. But the point here is that you can actually get very good localization results. For example, even without a LiDAR, but just using information from even a single camera in the infrastructure, along with the local IMU sensor and the visual odometry of the robot, you can get errors which are less than a centimeter out here. So having cameras also around in the infrastructure and on the robots, I think I believe that is good enough actually to do a lot of very interesting things, even including very precise localization. Just to kind of illustrate some other application of this robot is not able to see below in the floor. It has a LiDAR which is a 2D LiDAR which just scans. It's not able to see what is below it. Okay, there is an obstruction, its own body obstructs it. And so it crashes against things. But on the right side, because you have infrastructure cameras which are picking up the scene and they are mapping where all the obstacles are, the robot is now, even though it itself is blind, because it has got information from the infrastructure, it's able to plan its movement. So just to illustrate how the network and processing of the network really helps with this. So just to summarize, I do believe that the low latency connectivity with the on-prem edge is going to transform many, many verticals because you amortize the cost, the end devices become cheap. So I think it's a very exciting opportunity out here. And And the other important thing is that you can do things, the devices can work in a very collaborative way. And there are many, many open problems certainly out here. And of course, one of the challenges with AI-based approach is you need a lot of data. And again, my hope is that as a collaborative, we can actually create a lot of data sets for different verticals and make it available to the community. And of course, I can't do any of this work without all the students and staff in my team, and I thank all the funding agencies. So thank you.
I think we'll open for questions. I think there's one at the back.
Regarding, you had mentioned you need high bandwidth for images and all. So I was wondering if you have any ideas for the low bandwidth where network constrained environments like disaster recovery, if you have anything going on that.
Nowadays actually a lot of the edge devices, cameras, etc., are coming with decent processing capability, right? So, and you could actually do quite a bit of, inferencing right on the device and just send the extracted information. So I think that is quite possible now, and that's what I would actually do. Right? So I would reduce the requirement of the network by not sending raw images or even compressed images, but features which I extract from it, right? Only relevant features and send that across. Now, the problem with that, where suboptimalities comes is that now you're doing inferencing on an image from your own device. Whereas maybe if I had looked at multiple different images from different devices simultaneously, I could have done a better job of inferencing. But that is a trade-off, right? So for that, then I have to send more information to the central edge cloud versus just doing it at the edge.
We actually published a paper here as well on feature extraction. I mean, we extracted the free features and sent it on LoRa frequency. So that's what we did. And you made the point that I wanted to bring up. Let's say you want to do an image stitching of two images to get a collaborative perception of the entire scene. In that sense, have you worked towards, say, feature extraction from two different devices and then doing a feature fusion in this aspect of collaborative vision?
I have not done that, but I can see, it's a very interesting problem and how you could maybe train your models which are running individually on the edge to extract features with the view that, they will be stitched later on. Right? I mean, like one of the important things I would say is the representation should drive what it's going to be used for, and hopefully if you bring that in as part of your whole loss framework and then drive it, so upfront you design models which allow you to do that downstream task. So, yeah. Yes. That's right. That's right, yeah, of course, yeah.
Very nice talk. Just a couple of comments. One is, it's powerful to see a single representation giving you so much. When we have done situational awareness type things with multimodal data, we've had a small handful of representations. I'm just curious your thought process, where rather than trying to get one magic representation versus having a small subset, because then you can also enable a larger diversity of tasks downstream.
I think that is probably what we'll end up going to, because I think single one to handle all the tasks is going to be very tough in terms of compute requirements and storage requirements. As I said, but the thing is, how do I create a representation hierarchy where I have, I put in more and more capabilities in the representation, right, for enabling more and more richer, kind of information which gets encoded. If we could do that, that would be great. For example, if I am looking at a robotic application of just movement, a kind of so-called skeletal representation is good enough, right? I just need to know the boundaries of chairs, right, and because I want to avoid them. Whereas if I want to manipulate that chair, then I need to know where to hold the chair, right? And so if I can have a hierarchy of representations where I put in layers of more information, that will be great. And also some of the higher layers can be brought in as part of, almost like offline or lower latency, higher latency kind of feedback loops which are kind of munching and kind of digesting the information. It's like cognition, right? A lot of times we take in information, we haven't processed it, but later on we, in the night or whatever, we are thinking about it and we come to a better understanding. So I feel something like that will probably have to be done where immediately there are certain things we do, but the information or raw information is also there, which keeps getting digested. And you extract more information and kind of make it available. So yeah, and any ideas or thoughts from you, most welcome, we can discuss maybe. Yeah.
So what kind of sensor gives you these Gaussian slats as opposed to point clouds? How do you get them?
So the sensors themselves don't give you that. So the sensor is just a standard camera. So you get every pixel, you get red, green, blue color. Plus, you might also have a depth camera, so you get an additional depth information of where that particular pixel is. You could also get the depth if you had a stereo camera, where you can also reconstruct the depth of a particular, kind of what is called a voxel. So based on processing, as I said, the processing is essentially solving that optimization problem. You essentially figure out the Gaussian representation.
Great talk. Few times you mentioned availability of data sets. Could you comment maybe in the case of the warehouse example, which is it a perception data set or a movement data set? You want the robots to also learn how to move things around?
Not the movement data set. Actually, I would say it is around to drive the perception portion, right? So what are the different kinds of warehouses there are? What are the different kinds of, maybe what do you call it? Racks, pallets, boxes, objects, those kinds of things. Because eventually, besides movement, we also would like to have manipulation come in. And again, that is where this whole notion of physical AI, right? I mean, there's a lot of talk now about physical AI, where you are able to physically interact, and there is a lack of data. And the world is going towards, if people create foundational models, then that becomes the base on which we are going to do the. So can we get to creating foundational models first here in India, as opposed to waiting for a Google or OpenAI to do it?
It's a little side question, so I can understand if you don't want to answer it. So I see the value of digital twin has been well acknowledged, and there's no argument. The point is, people are developing their own digital twin for each use case, and even within each use case, like you might be doing your own similar everybody. Now to bring some kind of a master templates, or the way I like to use the term reference architecture for the digital twin of a particular domain or use case application, we need some standardization, and particularly on the data models and information models. Is anything being done on that? That is where, because then only we can use this, what you do here, for across different clients and everywhere.
We would love to actually drive that activity, right? I mean, we would really be happy to kind of work in a collaboration, and it has to be, driven in a very vertical specific way to begin with, where people care about it. It could be a warehouse automation or whatever, and then can we kind of develop the an open architecture, right, to address that question? I think. There is a digital twin consortium Rajat mentioned. I don't know whether they are doing work in those directions.
No.
If not, then
there is
maybe
going on in ISO IC JD 41, but that is still at a very foundation. So what we are trying to do there is come up with a digital twin reference architecture based irrespective of use case. Define some taxonomy, data model, some kind of structure approach. And based on that, then we can go to domain-specific use case application.
Right.
So I think even for that, what we need is top-down approach and then
bottom-up
use cases.
Right.
So that we have a seamlessness of the whole.
I know. Yeah. So we have worked a lot in the past on trying to do something similar for smart cities and so on. But one of the things I wanted to point out here is that there was a lot of emphasis on ontologies and data models and so on. The question is, how much of it do we want to invest time in creating that, as opposed to letting AI learn these relationships? But I do feel that there is need for some standardization, but it's a question of limiting the amount we want to standardize.
So I think ontology is more theoretical concept to be candid. I'm from a field, so I would rather say identify the standardize on data models rather than talking about taxonomy and policies and then coming to information model, data model. Data is what we need to crunch, and that's what helps. So let's straight away skip a few steps and get into data models, use standardized data models. I think we are through with a lot of problems.
I just want to give a partial answer to your question. There are consortium like Industry 4.0 which is developing standard. I don't know to what extent, but they have developed a reference architecture, concept of reference architecture, and there is some work that has been gone in that in the area which we can leverage. And that's one thing we can build on, but it's not progressed very much so far. Again, as you said, as Professor Bharat said, it has to be tailored to domain-specific use cases also.
Yeah, we'll take one last question at the back.
I come from the security background and I'm doing my research. I'm a research scholar working in the metaverse security. So I missed the initial part, but then I have a bit of idea what you were talking about. So what my question comes from, if we have the separate clusters of digital twins, the area is very specific to the medical scenario, but these different clusters have different weightage or cruciality of addressing particular clusters data or information is different. How do we create the twins and give the weightage for these twins to address the problem for a particular cluster, and also how we generalize for the whole network? I'm not sure whether I fully understood your question, but we can talk later. But just, it's kind of very similar to what Shivkumar was also asking about specific representations for specific applications versus kind of a generalized representation, right? So when you talk of clusters, I'm kind of assuming that's what you're referring to. I mean, different maybe different disease types, or maybe different medical equipment. I don't know. So, or it could be that you are extracting information from multiple different modalities, right? The same information, and so each gets represented with a certain uncertainty, right? And then when you fuse them, you have a certain weight which you need to use. It's the first one, like where we have different disease or different, type of information, not the similar. Right. So maybe we can take it offline and then.
Yeah, I think let's do that. I think let's please thank the speaker. Okay, I think with that we'll come to the end of the first session. Let's break for lunch. We'll come back at 2 o'clock sharp. Thank you.